Okay. Ordinary differential equations. What do you mean you don't tell me what you can share? That's crazy. Screen. There we go. Better. You won't let me share any windows. What were we gonna do? Second order, there's 3 types. They're for 3 different reasons. And I'm going to remind you what are some of the useful things to put on your index cards if you have them. But the main idea first is going to be looking back at the notes and reminding ourselves what the reasons for using the various methods are. So let me find those, because I did not prepare any material whatsoever for today, because for someone who has no finals, this has been an unreasonably busy finals week. Okay, second order, please load up faster. All right. Undetermined coefficients is convenient when you have only constant coefficients, because it just doesn't work otherwise. And then this is just a bad table. I don't like this table. So instead, I'm going to turn it in terms of when do you use particular methods? New share whiteboard. When would you use undetermined coefficients? Constant coefficient. So like if you have a y double prime plus b y prime plus c equals some function. Let's call it g of t. So we'll write undetermined coefficients. And that's when you can use undetermined coefficients. And that's a good way to think about when to use it. Let me see. We'll call it a t y double prime plus b t y prime plus c t equals d t and y1 . So using reduction of order is convenient when you have some crazy looking equation, but you know one of the solutions. In fact, it's basically the only thing you can do when you only have one of the solutions. So that's when you use reduction of order. Yes. Sometimes, yeah. So sometimes they don't give you any solution. But honestly, if you can get the complementary solutions easily, then you should just use variation of parameters. So if it's complicated, so if you have this crazy, so this is more of a when would you use it? Reduction of order is useful when you have some crazy thing that you can't get the complementary solutions for on your own, and you know one of them. But if you can get the complementary solutions on your own, variation of parameters is significantly faster than reduction of order. And it is really not necessary to use reduction of order. Yes, in which case, sorry. But she probably won't be like, I mean, she'll use not something that's worth using. But if you can get the complementary solutions and the right side is complicated, then you might as well use variation of parameters. So let me put a little caveat. If it's too hard to get the complementary solutions on your own, yeah, or if you don't know any YC yet, but it's too hard to get the complementary solutions. Wait, no, that doesn't make any sense. Like if you cannot get any complementary solutions on your own, use reduct. Yeah, there's really no reason to use reduction of order to get complementary If you're given no solutions at all, then you're either supposed to be able to get them using, get the complementary solutions and then plug them into some, like, if you can get them, you can use variation parameters. That's the idea. So I will now write, I'll contrast this to variation of parameters to make it clear what I mean. There, P, if you have something in the form, sorry, this should be, I forgot that this should be like CTY. Huh? Huh? Variation of parameters. Let me rewrite this as variation of parameters. Use if you can easily get both complementary solutions or both solutions are available. So that's my table for you. I don't like her table very much, but I think this table it just gives like an idea of like, when would you use each method? So if you have something where you can easily get both complementary solutions or they're already available to you, variation of parameters is the way to go. Reduction of order is only to be used in the worst possible case, when you have a solution given to you, but you can't really get the complementary solutions from scratch. And then undetermined coefficients only works in like technically very rare situations in functional space, which is if G of t is, the combination of sine, cosine, e to the whatever in polynomials. But it is also the easiest and fastest to do. And I can probably guarantee you that when she gives you the question where she says you can use any of the three methods to solve it, it will be a question that you can solve using undetermined coefficients. An undetermined coefficient is nice because it's just a system of equations that you have to solve, rather than doing some crazy thing with variation of parameters or otherwise. So we'll probably do one question each to get some practice on each and remind you of some of the pitfalls you might run into. Hello, Anna. We have created a cheat sheet, and by cheat sheet, I mean table of when to use each type of solution for second order differential equations. Undetermined coefficients, when you have constant coefficients, and G of t is in this special case. Reduction of order is only in the very sad case when you only know one solution and you can't get the other one for the complementary solutions. And then variation of parameters you should always use when you can easily get both complementary solutions or you have both of them available to you. This is quicker. It's just so much quicker. Yes, hi. So that must mean she believed you could get the complementary solution on your own. So it would have either been an Euler equation or a constant coefficient equation. Yeah, because those are the two situations where you can get the complementary solutions on your own. Is if you have an Euler equation or a not Euler equation, a constant coefficient equation, sorry. So if she asks you to do reduction of order and you don't have any complementary solutions, find them. And if she asks you to do variation of parameters and you don't have any complementary solutions, find them, because you can't not, or she would be a bad teacher, but she wouldn't really do that. Huh? Yeah, it wouldn't make sense for her to do that. So we will do some practice of each of them. We'll do one involving an Euler equation as well, just to remind you how to get that. I'll teach you how to do it without doing any memorization other than the substitution. Because remember, much of what we do in differential equations is put a clever substitution in and then plug and chug. That's what we practice in the first order section. So we'll do that again in second order. Let me pick a question from undetermined coefficients, and I'm going to make, I won't show the screen. I will just find it and then give that to you. Let me see. This one doesn't make any sense. Why did she write sine t? Anyway, this one's good. I'm actually going to do this one. Yes, because this one gives us all the basic pitfalls that you can get. Yes. One second. Okay, we'll do this one. Find the general solution to this problem, and I'll rewrite it better on this. So I'll rewrite it. Back to the whiteboard. I've already. We have the equation y double prime minus 2y prime. I need a better basis for my mouse than this one. It's too fast. Y double prime minus 2y prime minus 3y equals 4e to the negative e to the 3t plus e to the t cosine 2t. Sorry, cosine t. Hope you don't have any pens. Minus 2 sine t. So, does anyone remember what the first step is supposed to be? Yes, why do we need to find the complementary solutions first? Does anyone have any idea? Precisely. So let's think about this. So I'm going to tell you right now that e to the 3t is in fact a complementary solution. And let's think about why that's problematic. If e to the 3t is a complementary solution of this whole equation, what happens if we plug e to the 3t into this equation? If it's a complementary solution, it becomes 0. But if we want a 4 e to the 3t to appear on the right, how on earth are we supposed to get that if every time we plug e to the 3t into the complementary solution, it just gives us 0, no matter the constant? In order to come up with some kind of solution which will give us an e to the 3t, we need to introduce something new to e to the 3t that will enable us to solve, that will actually bring an e to the 3t into existence at the end. And the way we do that is by multiplying by t. So we'll talk about that in a little bit. Let's get the complementary solution real quick. Obviously r squared minus 2r minus 3 equals 0, which gives us r equals 3, negative 1. Nope, negative 3, 1. Nope, 3, negative 1. Yes, I'm just going to factor it, but I am right now. Yes, I don't know why I wrote that as not 0. I don't know what that is. I have no idea what I wrote there. Anyway, that means that r equals 3 and negative 1, and we therefore have the solutions yc equals c1 e to the 3t plus c2 e to the negative t. Yay, hurrah, one step done. And we can see that e to the 3t is therefore an overlap from the right side. And the problem with that fact is that we have an e to the 3t on the right side that we need to create out of nowhere. This is the reason that when we use undetermined coefficients, we need to figure out the form of the solution. And the form of the solution where there's a duplicate involves multiplying by t. So to get the form of the solution, we need to, so I'll talk about getting the form of the solution. We'll use a duplicate in a bit. But to get the basic form of the solution, you look at every term. We'll start with the easy term, and we compare it to our table. Our table, I will into the AT. I'll make a little table here. A e to the AT. Cosine or sine gives you a cosine t plus b sine t. And I'll give you a pattern for t cubed that'll allow you to do any polynomial. A t cubed plus b t squared plus ct. If you have either cosine or sine, then they both go to a cosine t plus b sine t. Yeah. I'll write this as cosine t cosine t. This is how they transform into what we call the form of the solution. The form of the solution is the thing that we can plug in to solve for the right constants. It's something which has coefficients, which look like, it has terms which look like what we have on the right. Huh? Maybe. It might be pretty quick. We'll see. We have 2 hours, but I also don't want to take infinite amounts of your time. So I will try and be quick at setting up the form of the solution. We'll do another way we set up the form of the solution. But so this is my little table that I have memorized. I wouldn't put it on your index card unless you don't remember. But we can take 4e to the 3t, and based on the table, we can turn it into ae to the 3t. But if you have a duplicate, that is, the complementary solution is the same as the solution, as something in the form of your solution, you need to multiply that whole thing by t, as many times as it takes to remove duplicates. For example, suppose that we had yc is actually e to the 3t plus t e to the 3t. We wouldn't suffice to write t e to the 3t here. We would need to write t squared e to the 3t to compensate for the fact that both t e to the 3t and e to the 3t are bad and mean. Sorry, by that I mean don't work, and they go away inside of the complementary solution. So this becomes at e to the 3t. And then in order to figure out a product, this is my method for a product. I figure out every possible multiplicative combination of the factors. I write them all down, and then I assign them coefficients. So you see that e to the t times blah, blah, blah results in 2 types of forms. Form number 1 is e to the t cosine t. Form number 2 is e to the t sine t. These are different functions, and therefore each of them deserves its own constant, b e to the t cosine t and c e to the t sine t. This way, for every single possible form that you need, t e to the 3t, e to the t cosine t, and e to the t sine t, you have a coefficient. None of this finagling where you plug in coefficients and multiply everything out. You just multiply everything out, figure out the different forms that you have, and then combine them all, and then get a constant that goes in front of each individual unique form. So e to the t cosine t is unique from e to the t sine t. Notice that the 2 doesn't really matter, the 4 doesn't really matter. What matters is the form of the solution is correct. That's the main pitfall with undetermined coefficients. She may have a question where you have to determine the form of the solution for undetermined coefficients, and I will show you how to do that next. But we will probably not solve this. Basically, once you've written this down, you can call this y of t, capital Y. And then you can plug in to left side, solve for all constants. And you're done. And James is right. We do not want to do this at this time because we have limited time and 2 other methods to index card out. If we have extra time at the end, then I'll probably go back and solve each of these. But the idea here is just knowing your table and knowing how to deal with complicated looking functions. I will now locate another more complicated looking function. Yes. Yes. Actually, wow. So my method is slightly wrong. Yeah, okay, great. So we will do this now. This one's actually a good one. This one's a great one for determining the suitable form. Lovely. This gives us all the pitfalls. So suppose we have y double prime minus 3y plus 2y equals t e to the t plus 2 e to the 2t plus sine t. Step 1. And does anyone have the complementary solution off the top of their heads? Sorry? That gives us r minus 1, r minus 2. This gives us r equals 1, 2. So we have yc equals c1 e to the t plus c2 e to the 2t. Now we need to figure out the form of the solution on the right. So when I told you to just multiply everything out and determine the constants, I was almost right. I'm right up to the point that you have a polynomial term like t in your situation. If you have something like t in front of e to the t, before you multiply everything out, you need to rewrite the t in your form. So there's a preliminary way that you write your form. You take every single factor that goes in your table, and you turn it into what the table demands. So t demands of us at plus b. And e to the t demands of us c e to the t. And e to the 2t demands of us d e to the 2t. And sine t demands of us e sine t plus f cosine t. All right, good so far? Now, these are straightforward. This is not. Once we get to this guy, if you were to multiply this out, you'd get AC t e to the t plus BC e to the t, and that's really weird, and we don't really need all those extra constants. So if you multiply this out, there's one way you can do it, is take all those silly constants and turn them into one constant each. Because what we're doing is not an actual mathematical operation. We are performing an inference. We're looking at the way the solution is right now, and we're saying, I don't like that. Sorry, no, sorry, that's not correct. I have to restart. We're looking at the right side, and we're trying to turn it into a possible solution, which, when we plug it in here, will allow us to solve for all of the coefficients a, b, c, d, e, f. So we don't need it to look like AC or BC. We only need it to look like A and B. E to the 2. But there is another problem, yet another one. If you notice, e to the t is a duplicate with the complementary solution. So if you see that, of course, you need to multiply this by t. But if you observe, t e to the t already exists. And so it's kind of a waste of time to introduce a t, unless you also introduce a t to a t e to the t and make it t squared. So basically, you need to make sure that when you deal with duplicates, like for example, b e to the t being a duplicate to e to the t over here, and you bring in a new t, if that term is already somewhere in your equation or your form, then you need to add a t to that part too. So this becomes t squared. So we get a t squared e to the t plus bt e to the t, and then we have e to the 2t is also a duplicate, so that becomes dt e to the 2t plus e sine t plus f cosine t. Does that make sense? It's a weird process, and it has its pitfalls, which is why some people don't like it and prefer to go for variation in parameters immediately. But variation in parameters does not like this at all. It's not pretty for variation in parameters. So it's probably best to use undetermined coefficients for a problem like this, if you haven't. But now we have the form of the solution. Do you have any questions about how we obtain the form of the solution? So this is the way. So the way that we figure out the form is we take if it's a polynomial, we turn it into its polynomial. If it's e to the t, we turn it into its. We use the table on every factor, both multiplied and added. And that's our first step. So we use the table on t to get at plus b, and e to the t, and e to the 2t, and sine t. Every function of t, yes. Whether it's multiplied or added, whatever, needs to be plugged into the table. And then you have to simplify afterwards. Yep. Okay, any other questions? I'm gonna need a nap after this. Okay, so yeah. Undetermined coefficients, you just need to do more practice. We might do another one later. We'll just do another quick one to remind you of the pitfalls. But if not, if you're ready, I'll move on to the more difficult ones, which are variation of parameters and undetermined coefficients. Variation in parameters requires a gloriously simple substitution. It is, just let me do a variable. If you have complementary solution, y1, use substitution, y equals v times y1, where v is a function. Use substitution, y equals v y1, a function. Everything else follows along from there. But it is complicated enough that I want to try and give you a set of steps that you can take after you have determined the substitution. Because basically you plug this in, you plug in this new thing for y, you solve for v after a lot of steps, and you plug it back in to this original equation to get y. So that is what we will now attempt to do for the problem. Which problem do I want to do it for? Not this one. That looks terrible. What about this one? Also looks terrible. Man, all of these are bad. Okay, we'll use this one. This one doesn't look. Wait, this is variation of parameters. What am I talking? Where's reduction of order? Here we go. Do I want to do this one? Or do I want to do this one? Or do I want to do this one? Well, this one doesn't look like it have any e's. That doesn't seem like a bad idea. Or do I want to do this one? That one looks terrible. No way. We'll do this one. Why not? So we will use the function, the equation t squared y double prime plus ty minus 4y equals negative 6t minus 4. Now, I have a question for you real quick. Sorry, this should be y prime. Can you get the complementary solutions for this equation easily? Or no? Not necessarily. It's an Euler equation. So if you really wanted to, all you would have to do is use the substitution, and we'll do one of these later. Oh, well, yes. So you can either memorize the equation. So there's two things you can do. In order, so first let's stop. This is an Euler equation. So we're going to get the complementary solutions. Euler equation. Euler equations have a t term in front of each y term whose power corresponds to the primes. There's no t here. In an Euler equation, you can either memorize substitution complementary solutions. Y equals t to the r, or equation. Well, you need a substitution no matter what, but to figure out what r is, you can either plug in the substitution directly and play around with it, or add a r minus 1 plus br plus c equals 0. Note. And y equals t to the r. So you can either just memorize the substitution and plug it in and you get this equation, or you can memorize this equation and the substitution and immediately get what the two solutions for y are without having to derive this equation from scratch. One of my friends, Robert, who is a math major in this class, decided to just memorize the substitution y equals t to the r. And he ended up being able to get everything done with just that substitution in his head, because he didn't really have the mental energy to memorize this equation at the time. So worst comes to worst, but you have an index card. So why wouldn't you memorize this equation? And by memorize, I mean write it down on the index card. So you can just do this, and that gives you the two solutions. But we are told that, so that's just a little box on the side. But we are told that y1 is equal to t squared. So we can use reduction of order. Reduction of order involves the substitution y equals v, y1 is equal to v t squared. So step one, plug it in. Y equals vt squared. Y prime equals v prime t squared plus 2tv. Y double prime equals v double prime t squared plus 2t v prime plus 2t v prime plus 2v. Which is equal to v double prime t squared plus 4t v prime plus 2v. And now we can plug all that into here and see what happens. The magic is going to occur. It's going to be beautiful. For a given definition of beautiful. We are going to plug everything in to get v double prime t to the fourth plus v prime 4t cubed plus 2 plus v 2t squared. So that's that first term t squared y double prime there. Then for ty prime, we'll plug in y prime. So this is plus v prime t cubed plus v 2t squared. So I plugged in y prime into ty prime. Y prime, that's the derivative of y. So y is our substitution. So we've just determined the derivative of y. We use the product rule, v and t squared. Does that make sense? Okay, great. Yeah, because the derivative of v is v prime, because v is a function. Yeah, I have to figure out the two derivatives, and then I can plug them in to my equation, which is what I am now doing, is plugging them in. V 2t squared. Finally, minus 4v t squared. Now, the clever bit is that all of your first order terms will disappear. This is equal to negative 6t minus 4. So you can't forget to write that. Let me write all first order terms disappear. And we are left with the equation, because vt squared plus v2t squared, let me do it another color. v2t squared plus v2t squared minus 4vt squared is 0. So we are simply left with the equation v double prime t to the fourth plus 5v prime t cubed equals negative 6t minus 4. Exciting? Excited? Hurrah? I don't know. So now it's time for step 2. W equals V prime. W prime equals V double prime. And this becomes W prime T to the 4th plus 5. Let me just reorder this bit. T to the 4th W prime plus 5T cubed W equals negative 6T minus 4. Exciting! The reason this is exciting is because it's a first order linear differential equation, and we have the general solution for it forever in our index cards, theoretically. So as long as we put this into standard form, we can simply plug it into the general solution and immediately, and by immediately I mean with some ardor, get our solution W. So I don't know if any of you want to do that on your own before we start, or if any, but I will write down the general solution equation on the board here. W is equal to the integral of mu g dt plus c over mu, where mu equals the integral, equals e to the integral p dt in w prime plus pw equals g. And note that I've just replaced y with w in this case. So this is the general solution to a first order linear differential equation in standard form. W prime plus pw equals g gives us w equals the integral mu g dt plus c over mu, and mu equals the integral e to the p dt. So we will rewrite this equation on the next page, but I'm going to divide out t to the 4th. So on the next page, we have w prime plus 5 over t times w equals negative 6 over t cubed minus 4 over t4. We can determine that mu is equal to e to the integral 5 over t dt, which is, of course, e to the 5 ln t, which is t to the 5th. Now we know what g is. This is g. So I'm gonna put a little this right. Let me do it in another color. This right here is g of t. So we can plug everything into the equation. W equals the integral of mu g, so t to the 5th, times negative 6 over t cubed minus 4 over t 4th dt plus c all over t to the 5th. This is mu g, this is mu. This is equal to the integral of negative 6t squared plus 4t dt. I pulled out the negative over here, plus c over t to the 5th. This is equal to negative 2t cubed plus 2t squared plus c all over t to the 5th. Agree? Any questions? Sorry, I feel like I've rushed a lot, but we're almost finished with W. With getting the expression for W. What? Yes, you have to divide out anything in front of W prime to get it in standard form for the general solutions. That's why I wrote in W prime plus BW equals G. This is what you need to be able to use this. So now we have, yes, sorry, hello. Ah, yes, you are right. Thank you for reminding me that this minus distributes into the equation. That's probably pretty important. Probably, just kidding, it is important, obviously. Okay, hello, yes? You have a question? Okay, so this can be rewritten as W equals -2 over T squared minus 2 over T cubed. Let me write this better. T squared minus 2 over T cubed plus C over T to the 5th. Now we have W. You may be wondering, why the hell are we doing this again, Jonas? Where did this come from? If we look back at our step 2, we wrote that W equals V prime. So we will now write our next step, which is, funnily enough, W equals V prime. I'm writing in here again because this reminds us that we need to get V out from W. So if W equals V prime, then V equals the integral of W dt plus another constant, let's call it C2. So we have to integrate this. Now the integral of W, I'll put a little integral sign to show that we're doing it, is, I have to do this bit by bit. I'm doing it all in my head, just to speed up. You know what? Maybe I'm wasting time. So this is 2 over T. And then -2, T to the -3. Oh, do you already have it? Yep, plus 1 over T squared. Yeah, that's right. The C, it can be absorbed into the C again. So all of our weird extra numbers can be absorbed directly into C. Yep, so we can just write this as C over T to the 4th because any weird constants we get can be absorbed into C. But if you just integrate it, you can put the number there if you want, just absorb it in later. One of the other tricks that you do all the time in ordinary differential equations is absorbing things into constants. The constants are hungry. They will eat your soul. But yeah, so I'll write this as C1. And then we put a C2 here. Okay, now we have, this is an integral. Yeah, this is just a sign for I did an integration to it, and I didn't want to write integral all of this again because I'm skipping steps, sorry. But once you take the integral, you have this is equal to B. Now all that remains is to recall, and this is step 4, y equals V by 1. Or let me just write it in nice color. And we know what y1 is. It's T squared. So y is equal to Vt squared is equal to 2t plus 1 plus C1 over T squared plus C2 T squared. And that is the entire solution y. And we are done. This is the complementary solution. That's the clever bit. You only need one complementary solution to get all of them. That's why the constants are there. The constants show up in the process and they give you the complementary solutions. So C1 over T squared and C2 T squared are the complementary solutions. And we can check right here that this is correct. So we have done it. Those are our steps. Step one. So step one is step 0 is remember the basic substitution y equals Vy1. Step 1 is to plug it in so that all the first order terms disappear. Step 2 is to note that W equals V prime and W prime equals V double prime. And then you can solve this differential equation for W. Then you remember that W is equal to V prime to get V, and that Y equals Vy1 to get Y. So you're basically stepping down into the first order, solving it, and then stepping back up out into the Y. So that we get the solution there. If you wanted, you can, I would add some extra steps here. I want to write things down in case you're going to put them. Solve for W. Wow, that's terrible. That way you know that once you plug in W equals V prime and W prime equals U double prime, you know you have to solve for W. That's kind of the extra step you need to. Once you solve for W, then you can step backwards into steps. So plug it in so that all the first order terms disappear, then use the substitution W equals V prime, W prime equals V double prime, and solve for W. Then integrate W to get V. And then, so I'll rewrite this one here as integrate W to get V. And then step 4, Y equals V. That's another way of writing it. So those are different ways of thinking about the steps. So I tried to put it in a step-by-step method because it is a really long thing, reduction of order, but it is straightforward, but it's easy to get lost in it because you forget what you were originally doing. And what we were doing all along is trying to solve for V so we can plug it back into Y equals V, Y1. Any questions? Hello, yes, James.
Our original fix was 2 squared y double prime plus 2y prime minus 4y, right?
Equals -6t minus 4.
Okay. That, I think you solve it out, you end up with a repeated, complementary solution.
False?
But because then,
I don't know.
well, yeah, r times r minus 1, the r squared minus r plus r minus 4.
R squared minus R
Plus r.
minus 4. Oh. Equals 0. Well, yeah, that gives us R equals plus or minus 2. Yes. I actually forget what you have to do in this. This is a good reminder. Thank you for reminding me that we need to find out what to do if you have a repeated solution. Stop doing that. No, I don't want. No. Euler, please tell me how to do it. Euler. Oh no. If there's a repeated root, you have to use reduction of order to get the new answer. Huh?
We'll write it on the end first.
Well, oh. Wait, is this Euler? No, this isn't Euler. What am I doing? Where's is it, where is it? Okay, thank you. Thank you so much. You have saved me from wasting my time. Why is it after higher order linear? Who thought this was a good idea? No, wait, yes, okay, lovely. Okay, I was like, that doesn't make any sense. Yes, okay, so it turns out, in fact, you must find the other by reduction. Oh no, it's just ln x. You just have to put an ln x there. with the second solution. Okay, let me just write that down. Don't ever, if I doubt she'll give you a situation where you have complex roots for an Euler equation, because that would just be mean. And she is not someone who's like, you must memorize things. So I would, is she? A little bit? All right, well, I just don't remember her doing this. So if you really want to, you can write down the general solution for a situation where the complex roots are lambda plus I mu, but focus on the two, let me write these on the actual whiteboard because whoever's watching this and the recording has no idea what's going on. So if you have an Euler equation, AT squared y double prime plus BT y prime plus CY equals 0, then the complementary solution can be found using the following equation. AR minus 1 plus BR plus C equals 0. If R1 is not equal to R2, then YC equals C1 T to the R1 plus C2 T to the R2. If R1 equals R2, YC equals C1 ln T. Let me write this as T to the R1 ln T plus C2 T to the R2. So that ln gets introduced. And that's probably what I'd write on your index card if you had time, if you had space for an Euler equation. But you probably won't get this scenario. And by, I'm not going to tell you that you won't, but hopefully you never do. But if you do, it's on your index card. If there's space. Okay, it's probably time for variation of parameters now, but I'll give us a sec for, actually, usually, well, we've been at this for an hour. So it is now time for us to take a 5-minute break because that's better for learning. So I'm going to pause the recording and go to the restroom. And I will be back. And hopefully you will have stopped thinking for at least 15 minutes so that you can be refreshed when I return. Man, I'm so tired. And we'll do variation of parameters of what you should write in your index card. In that case, yes, hi. This one? Red? No, this one. This is what we did. Yeah. Okay, I'll be back. There's more people here. I'm just kidding. Okay. It hasn't been 5 minutes yet. We have one more. Hi. What? Huh? Who teaches linear algebra? Usually Dr. Marks. He used to, but I don't know if he does anymore. Dr. Marks is reasonably good at. Okay, stop. Wait, no. I can never tell you who's a good teacher. Do not listen to me if I tell you who's a good teacher, because I don't really listen to any of them. So never mind. But he sounds nice. He's probably good. And I don't think he has any exams for linear algebra. Only take-home quizzes and homework. So yes. It is a interesting and very useful class, and you will always need everything in it forever. So that's my recommendation for the class. Very important for all people. Yes? Maybe, yeah, because it's really important. It's just so useful. There's so much that we do with it. And I'm probably overstating it, but I'm not. Dr. Wolf is a wonderful teacher. Not just for anything positive that I do about Dr. Marks, but we're taking an extremely difficult class, complex variables, and he's been trying his darndest, but people don't necessarily really understand the subject matter. So that's kind of what I've heard about Dr. Marks. But I think some people are understanding it. So I don't know. Okay, I'm going to return to, did I never? Oh, I just recorded the whole time. Sorry, everyone who was, I pressed pause share, not pause recording. Well, it's okay. I'm not gonna edit it out. People can just skip forward 5 minutes when they realize what I did. Resume share. It's time for variation of parameters. Yes. Actually, you know what? Maybe I'll just show you. Watch what happens when I plug in the substitution, t to the r. If y equals t to the r, which is our basic substitution, then y prime equals rt to the r minus 1, y double prime equals r minus 1, t to the r minus 2. Now let's plug it in. A t squared r minus 1, t to the r minus 2, plus b t r t to the r minus 1, plus c t to the r equals 0. Now note that t squared times t to the r minus 2. What is that? Does anyone know? T to the r. Yes, agree? Because you add the exponents together. R minus 2 plus 2 is t to the r. And t times t to the r minus 1 is what? T to the r. So this can be rewritten as a r minus 1 t to the r plus b r t to the r plus c t to the r equals 0. And you can cancel out all the t to the r's to get a r minus 1 plus b r plus c equals 0, and then solve for r. Does that answer your question, or was that not what you were asking? So what I mean by skip is that if you just memorize y equals t to the r and not this equation, then you just derive it on the fly. Yeah, but for some people, memorizing this is really hard because it doesn't make any sense at all. But for some people, memorizing is perfectly fine. And during exam 2, memorizing this was not something my friend had time for, so he just memorized this and it was fine. He actually got the credit on that Euler problem. He was like, what? That's impossible. And I was like, no, you did it somehow. So yeah, so you can either memorize this and just do everything, or you can memorize this. But by memorize, I mean put an index card because you have one. And I'm really trying to reduce the amount of things you put in an index card is the thing though, because you have only a 4x6 index card to bring in. So the less things you put on it, the more compact you can make your knowledge, the better. But deriving on the fly is also slow. So you kind of have to balance out how fast would you be able to do this in the exam? Or can I fit this with reasonable space on my index card? Where was that? Yes. Uh-huh. Well, t to the negative 2 is 1 over t squared. So this is yc. Do you agree? This is also yc. Because t to the negative 2 is right here. yc. yc. Do you agree? Yes, that's the clever bit of reduction of order. But it gives you not only the other complementary solution, but also the particular. As long as you have a single complementary solution, you can topple the whole thing over like dominoes. Yes. If you had an imaginary root, I don't think you would enjoy your life very much, though.
That would be nice.
Good. She won't do it for Euler. She won't. I really don't think that she will. That's no, that's reduction one. Euler is just a form of this thing. Yeah. The shortcut is either this thing or this thing, which gets you this thing slowly. So it's a certain type of equation. Reduction of order is a method of solving an ordinary differential equation when you have access to one of the solutions. Yes. Okay, so I will now proceed to the next question, type of question, if you don't have any other questions, but only if you don't have any other questions. Yes, it would have just been more difficult. Precisely, preferably the easier one. Oh, sorry, even I make mistakes when teaching. That is another way of thinking about it, yes. But sometimes you're just given one solution and you can't figure out the characteristic solutions at all. And you just and you just have to figure everything out from that one solution that you're given. Because maybe that's variation of parameters. Because variation of parameters uses both elements of the complementary solution. And it is what we will now discuss. But reduction of order only requires one piece. And it's useful when some clever guess has discovered for you the first piece. Or you have the character, or you were given the first piece for some reason. Okay. I will take us to variation of parameters. In variation of parameters, I'm going to write it with the text tool. If you have y1 and y2, then yp equals u1 y1 plus u2 y2. And u1 and u2 can be derived from the following system of equations, which it is vitally important that you put on your index card. y1 u1 prime plus y2 u2 prime equals g, and y1 prime u1 prime plus y2 prime u2 prime equals, sorry, 0 g. Solving this system of equations is slightly more difficult and requires the use of either memorizing Cramer's rule. Cramer's rule is a very nice thing to memorize, but if you have not memorized it, then you will need to put the following three things on your index card. W equals y1, y2, y1 prime, y2 prime. W1 equals 0 g, y2, y2 prime. W2 equals y1, y1 prime, 0 g. And u1 prime equals w1 over w, and u2 prime equals w2 over w. And this is everything you need to know for variation of parameters. As long as you can solve determinants, you are good. Also, g is the, if you recall, it's the right side of the equation, the differential equation in standard form. So as if you have y double prime plus p y prime plus q y equals g, then you can use this. So the reason I inform you that learning Cramer's rule is nice is because learning Cramer's rule allows you to eliminate all of this stuff from your index card, because this is simply derived direct, all of this stuff actually, this is derived directly from Cramer's rule. But if you do not understand Cramer's rule or have the time to memorize it, then you had better just put all this stuff on your index card if you have the space. Cramer's rule, I guess I have time to tell you Cramer's rule. Cramer's rule is a method for solving any system of linear equations. If you have the following, ax plus by equals c, and dx plus ey equals f, Then you can solve this by the use of three determinants. We have D, which is called the coefficient determinant. It has the coefficients of the variables, A, B, D, E. Then you have the variable determinants. Dx represents, is the determinant for variable x. And in the determinant of variable x, you take D and you replace it. You replace the coefficients of the first variable x with the constants, C, F, B, E. A and D are the coefficients of x, and they can be replaced with the constants C, F. Dy is similar. You keep the coefficients of x, A, D, but you remove the coefficients of y and replace them with the constants, C, F. And then y equals dy over d, and x equals dx over d. My math book told me to memorize this years ago, and it has served me well to this very day. You used to learn it in circuits, but we didn't have time to teach it. So you didn't learn it in circuits. But it is a rule that is very general and useful. And if you the only reason I would tell you to memorize this is if this made more sense to you and you could put this into your head easily, more easily than you had space to put all this stuff in your next part. Because you can observe that the Wronskian determinants here are derived exactly from Cramer's rule. W is the coefficient matrix. W1 is the coefficient matrix where y1 and y1 prime are replaced with 0 and g, quote unquote constants. W2 is the coefficient matrix where the coefficients of u2 prime are replaced with 0 and g. So you can either write all this stuff down, or you can somehow make sense of Cramer's rule and then apply it to this system of equations. And those are your two ways of being ready for variation of parameters. But we will do a problem in a sec. Does anyone have any questions though about variation of parameters or Cramer's rule? Okay, we will do a practice problem. Thankfully, there's basically no steps involved. You just write all the stuff down and plug and chug until you're done. Once you have u1 prime and u2 prime, you of course need to get u1 and u2. You can actually ignore the constants. Yes, you can ignore the constants when you, so u1 prime, u1 equals the integral u1 prime, and u2 equals the integral u2 prime. Ignore constants. Don't add, no, sorry, no need to add. Yeah, great. Okay, problem time. This one looks bad. I don't want to do it. This one looks mean. Let's just do this one. Well, we'll see. Have I done this really? I have. Well, it's fine. We'll just do it. So we will begin by drawing this, the big, we're gonna write it and then we're gonna put it in standard form because it needs to be in standard form to make this work. Okay. Give it to your team. In order to write it in standard form, we divide everything by t. So this is 2 over t minus 2 y prime plus 1 minus 2 over t y equals e to the 2t over t. So y1 is equal to, according to the problem, e to the t. y2 is equal to, according to the problem, e to the t over t. And g is equal to e to the 2t over t. Do we agree? G, sorry, I'm really bad at writing G's. I need to find a better way to write them. But we were told what they were. So we are told, let me write a little text that says given. Yeah. Yep. And then G equals e to the 2t over t. Whatever's in front of the y double prime, yes. In order to use variation of parameters, it has to be in standard form. Okay. So now we go back to our Wronskians. If you are deciding to write down the Wronskians on the index card, then you can just skip the system of equations and not bother with it. And you only need to draw these Wronskians on your index card, just this second half. So you can either memorize this or you can memorize this, but you definitely have to have this. So this is, I'll put a little star here. It's super neat to have it. But you can either memorize this or memorize, this bit here. Okay, so we will start plugging in to the Wronskian. First we need y1 prime, that's of course equal to e to the t. And we need y2 prime, which is equal to e to the t over t minus e to the t over t squared. You may be wondering, how did you get that? I used the product rule. E to the t times t to the negative 1 gives us e to the t over t minus e to the t over t squared. And now we can determine each Wronskian. Wronskian equals y1, y2, y1 prime, y2 prime, e to the t, e to the t, e to the t over t, e to the t over t minus e to the t over t squared. Do you all remember how to evaluate a determinant? It's cross 1 minus cross 2. So this is equal to e to the t over t minus e to the t over t squared minus e to the t over t, which is equal to e to the 2t over t minus e to the 2t over t squared minus e to the 2t over t, which in exciting news means that this is simply equal to negative e to the 2t over t squared, which is probably going to make everything easier. So this is W. And I have taken up so much space and now I have to move to the next page. People are writing things down, so I'll give you a sec. Okay, now we will do Wronskian 1 and 2 on the next page. Wronskian 1 is, of course, 0g, y2 prime. We know that g is e to the 2t over t. So we have 0 e to the 2t over t, e to the t over t. And then I'm actually not even going to write because that's going to be multiplied by 0. And I don't want to write everything there. So this is just equal to negative so this is 0 times blah, 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 minus e to the t over t times e to the 2t over t, which is negative e to the 3t over t squared. Then it will be time for Wronskian 2, which is equal to y1 prime 0 g. This is equal to e to the t, 0, e to the 2t over t. And this is equal to e to the 2t over t minus 0. Any questions so far? I know I've gone as fast as possible, but most of this is plug and chug. Almost all of it, in fact, is plug and chug, as long as you write down the correct things. So I just want to remind you, I'm mainly focusing on what do you need to write down in your index card. And now we're just filling it out. So you have some practice plugging in to the index card. Now we want u1 prime, which is equal to w1 over w, which is equal to negative e to the 3t over t squared all over, what's w? Negative e to the 2t over t squared. And if we fix this nested fraction, the t squareds cancel out and the negatives cancel out. So we're left with e to the 3t over e to the 2t, which is just e to the t. And therefore, u1 equals the integral of u1 prime, which is equal to e to the t. Any questions about that? Now, u2 prime is equal to w2 over w, which is equal to e to the 3t over t, all over negative e to the 2t over t squared. We should probably use nested fractions here. So this is t squared over e to the 2t times e to the 3t over t, which is equal to negative t e to the 3t e to the t. Now you may be like, oh no, you have to use integration by parts for this, but you don't, because you're going to bring your integral tables to the exam, right? That's the one thing. And your Laplace transform tables. And so your integral tables should tell you that the solution, if you try, so this is equal to u2 prime, and then u2 equals the integral of t e to the t dt. And I happen to know from guess and check that this is equal to negative t e to the t minus e to the t. And that gives us u2. So u2 equals e to the t minus t e to the t. Very exciting, almost done. We're about to win. Because all that remains for us to do is to plug in u1 and u2 into, oh God, into this, which will give us y particular. So I'll rewrite that over here just so we know what we're doing. Sorry, I know I'm skipping and you can't see anything. I apologize. Yp equals u1 y1 plus u2 y2. And we know what y1 and y2 are from here. And we know what u1 and u2 are from here. So y1 is e to the t, u1 is e to the t. Y1 is e to the t, u1 is e to the t. So this here is e to the t, e to the t. And then u2 is all of this mess. And y2 is e to the t over t. So this is e to the t over t times e to the t minus t e to the t. This is yp. And now we can further, let me use this as a negative sign. We can further simplify this into e to the 2t plus e to the 2t over t minus e to the 2t, which is simply equal to e to the 2t over t. And that is our particular solution. And our general solution is, of course, yp plus cy1 plus c2y2. And we already have those, so I'm not going to bother writing that in. But we are done. Let me just make sure this is right. It is. Yay. We did it. And now it is 7:02. Does anyone have any questions about variation of parameters? That is everything second order then. What I am going to be doing on Wednesday is all the exotic stuff. I have done many sessions on Laplace transform at this point, and I think all of you have been here for various numbers of those sessions. Yes, I have seen you all for Laplace sessions. Okay, great. So I will probably hone in on the more exotic. I'm going to have 2 one-hour sessions based on all the different disparate times that people told me they could attend. And I'll probably hold them both in the conference room, but I haven't figured out if I can do that yet because I forgot to ask Peggy and I haven't had time. Again, for someone who has finished their finals, I have been unreasonably busy. I have been everywhere all day. Some of you have seen me in some of those everywhere places. So I have been busy, but I will get those times out as soon as possible. Yes. And if you would like to utilize me for the next 30 minutes to ask any of your questions about the exotic stuff on the exam, I am here to do that too, because I do have 30 minutes, but I don't want to extend your time past when you would like me to extend it. So if you want me to do anything exotic, let me know and I will inform you about things. And if not, then we can go. Yeah, let me check. Mail.
Number 1 and number 3, so double step 4, and then direct delta, and then convolution interval.
Yeah, so she said, use Laplace transform to solve initial value problems with continuous or piecewise continuous, which means you need the unit step function. Oh boy. So like number 1 and number 3 are problem set 4. Then the more exotic quote unquote things that I can reteach is computing the Laplace transform of the delta function and convolution functions and writing an nth order linear equation as a system of n first order equations. So those will basically be repeats of my previous tutoring sessions, which some of you may have been to or may not have been to. So you can go to those if you wish tomorrow, or you can not go to those. I don't think I'll really have time to reteach how to use the Laplace transform to solve initial value problems, because it's so much, and I have done it so many times, and I think all of you have been to those. So worst comes to worst, I will make some kind of video and upload it so that people who don't know can watch that. But if you don't know and you've already passed problem set 4, I am very sorry for your loss. But that's me talking to the Zoom. I know that. Oh, was okay. Okay, well then maybe we will go over those then, because the nth order is very, very straightforward. Okay, well, if you're going to be attending then tomorrow, then I will know what to do. I will hone in on section 6.5 and 6.6 first. And if there is time and people do not want work on this bit, then I will do the Laplace transform for initial value problems. Okay. Well, we can just stop. I'm going to stop my share, and then I'm going